All right, so I think the quiz should have been straightforward. Any questions on the quiz? I think it was just a question on one of the worksheets, maybe? I can't even remember. It's been a busy few days. All right, so let's go back to what we introduced last time, which was hypothesis testing. So instead of starting with hypothesis testing in general, I tried to start with an example of why we might want to do this, and then let's just recap that example in a few minutes, and then we'll go on to the general case of defining some terms and doing hypothesis testing more formally. So, well, before I go through this and start blabbing, does anybody have questions about last time? I'll just talk then. So, last time we talked about a really simple example, like we're being given a coin and we want to know whether it's fair or not. So that's what we have here. We want to test whether a coin is fair. So there's no God telling, well, maybe there's a God, but there's no God telling us the coin is fair, right? Or the coin has probability blank of being heads or tails. So we don't know. We have limited information. And what we want to do is try to test whether it's fair. And so by fair, I mean the probability of heads being 1/2 or the probability of tails being 1/2. Those are the same things. And maybe just a note, so we'll see a little bit more about this soon, but I'm choosing a silly coin flipping example right now, but as you can imagine, you can use hypothesis testing on a whole slew of different real-world examples. So it's used a ton in all over the place, especially in the medical field. So a lot of times people want to test whether a drug is successful at curing some disease, say, and you might start out by testing the claim that the drug has, say, no effect. So your claim, instead of something silly like the coin is fair, your claim might be something like, this drug has no effect on disease X, whatever you happen to be testing with respect to. And then you carry out some experiment, you do some procedure, and you find out that, well, maybe this drug does do something, right? It does seem to cure a lot of people, or it doesn't, and you try to find out if that's statistically significant. So that's sort of this whole body here. So all that just to say that this does have real-world applications. All right, so what's the procedure for hypothesis testing with respect to this specific example? So first we assume something, some distribution of probabilities. So we assume that the coin is fair. And I started to say at the end of last time, this is what we're going to define as the null hypothesis. And the null hypothesis is just a claim, so I'll write this in a minute, it's just a claim about a parameter with respect to this process. So the parameter here is the proportion of heads to tails, proportion of heads to the total number of flips. All right, so we assume that this is true. We assume the coin is fair. And then we conduct an experiment. And we conduct the experiment assuming that this is true. So what was the experiment? What do we do? What do we say? Yeah, so we flip the coin and we decide, well, how many times are we going to flip it? 20, 50, 100? And why might we place restrictions on the number of times we flip the coin?
Time, money.
Yeah, so in this case, we might not want to sit here and flip a coin for the next hour or the next hour, right? We might not want to flip a coin 1,000,000 times, so we'll just fix the number and do it. So in real-world cases, say where drug companies are testing whether a drug has a significant effect with respect to some disease, what might be the restrictions there?
Human patients.
Yeah, so you could imagine maybe cost would be a restriction. You want a large enough sample so that you get good numbers, you really get to know whether the drug is significant in curing some disease, but at the same time you can't spend all of your money rounding up people, giving them free medication, monitoring them, recording all this stuff, paying statisticians to do the hypothesis test, right? So you might not want to use 1,000,000 people in your survey. You might want something small, just like we don't want to sit here and flip a coin. All right, so we conduct the experiment and then we calculate some test statistics. So in this case, since we're dealing with a proportion, then we calculate the sample proportion. So this is the same sample proportion from when we talked about estimators, point estimators, and interval estimators, right? So how would we calculate this? just as a review? So what does p hat equal to in general?
Proportion, so it's over, number of successes over the number of trials.
The number of successes over number of trials. And so in this case, the natural thing to do is define a success as what? Getting a heads, right? And you can do this whole experiment where you just replace heads with tails, right? Because it's 50-50, it would be the same thing. All right, so you calculate the test statistic, and then you assess whether the test statistic that you calculated is rare under the given assumption, so under the assumption in 1. So what test statistic might be rare under this null hypothesis?
You get a whole bunch of tails.
Yeah, so one test statistic that might be rare would be something like, so say if you flip the coin 20 times and you got 19 heads, wouldn't that be rare if your coin is fair?
Yeah.
It would be very rare. So you guys should be able to, in theory, calculate the probability that you get 19 tails and 20 flips, right? And it would be very low. And same thing, if we got a lot of heads, that would be very rare. But how are we going to define, how are we going to set a line between what is rare and what's not rare? So what if we flipped it? Yeah, so we're going to use things like the things that we use in confidence intervals, so it's going to take into account the standard deviation, the spread of the distribution, in order to understand what's rare. So you could imagine that if we got p hat as something like 11 over 20, so in our case p hat was 11 over 20, meaning we flipped it 20 times and we got 11 heads, this doesn't seem to be rare. So if we assume that the coin is fair, and this turns out to be our test statistic, well, can we reject the claim that it's fair?
No.
No, it doesn't seem reasonable to do that. Right? What about 13?
No.
It doesn't seem like this is very rare either. And
No.
this is actually some review from chapter 7.
17 over 20 would be more rare than 13 over 20.
So, yes, right. So remember that the sample proportion is distributed normally, right? And so in this case, if we did this experiment, if we did 20 flips of the coin, 10 out of 20, or 1/2, would be in the middle, right? And as you get further and further out here might be something like, 17 over 20. And over here might be something like 5 over 20. So these things seem like they're getting more and more rare. It's possible, right? The probability isn't 0, it's something positive, but it's low. It's a lot lower than 1/2. So if you do find out that this thing is rare, well then you might have evidence against this assumption. So if you calculate a test statistic and it turns out that that test statistic is rare with respect to the assumption, then you might reject this assumption. So you could say you have evidence against it. And if it's not rare, then technically all you can say is that you don't have evidence against the null hypothesis, against this assumption. So some people say, well, you have evidence that it's true, but to me that seems like you're claiming too much. So if you want to be modest, and we want to be modest, we say we don't have evidence against it.
Was there a difference, I guess, in here, like evidence versus proof?
Yeah, so more than you want to know. Yeah, so this is a good question though. So say we get a test statistic 20 out of 20. 20 heads. We flip the coin 20 times and we get 20 heads. Is this proof that the coin is not fair?
No.
No. Why?
Because I could do it and get something completely different. With the same
Well,
exact
so say
coin.
we just flip it 20 times. We don't know anything else. Just with this piece of information, can we say this is proof
No.
that?
No.
So no.
It's not proof, but it's evidence.
So it's really strong evidence, right? But and I'm reserving the word proof to mean something like absolutely certain that it's not. And so why can't you say that it's absolutely certain that the coin is unfair based on this?
We can keep flipping it, we get
The probability of that is zero.
That's why. So the probability of this, under the null hypothesis that the coin is fair, this is not zero. And I think I fooled some of you with this on the first exam. I asked you a question like, what if somebody flips a coin over and over and over again and they get heads a whole bunch of times? Is it still possible that they, are they due for a tails on the next flip? So no, they're not, right? The probability is equal every trial. And so this probability, it's possible for you to get this under the assumption of a fair coin. So it's not proof against it, but it's really strong evidence, right? This is, if you were willing to bet that the coin was unfair and you got this as your test statistic, it would be a really good bet to do so. And this all goes back to what we talked about in the first day with inductive reasoning and deductive reasoning. So maybe it's ringing some bells, I don't know. All right, so this is the procedure specifically for this example. So let's look at the procedure in general. So hypothesis testing in general. And so we're going to need a few definitions first. So the first one is going to be a null hypothesis. So we're going to formally talk about this first statement over here. So a null hypothesis is, so I can't remember if your book calls it this, and I think your book has a definition which I didn't like as much as actually what Wikipedia had to say. So this might actually be from Wikipedia, but it's good. So it's a statement expressing a default position about a parameter. So, well, we should know, so a statement or a claim, we might use these words interchangeably, so I'll put it up here. So a claim is just a factual statement. It's a statement that can either be true or false, right? So a null hypothesis is a statement or a claim expressing a default position about a parameter. So first, what is a parameter? To drill this into our heads. A what?
Something with population between 2
Sure. So it's a value, a characteristic of a population, as opposed to a what?
That is an example.
A statistic, which is about a sample. So, and this says it expresses a default position about a parameter. So what does that mean?
Like that's where you're starting from?
Yeah. And this is interesting. I mean, how do we know what the default positions are? So in this case, what was the default position? Yeah, that the coin was fair. So why did we choose that as a default position?
This is smart.
I don't know why. I mean, it's sort of an interesting question to wonder why we would choose it being a fair coin as opposed to it being some other distribution. You have to just choose one in order to do a hypothesis test. So it seems like fair is a decent choice.
Glass is half full versus half empty.
Maybe. So, I mean, if somebody confronted you and say, well, why did you start with 1/2? Why didn't you start with 1/4 for head? If you really got into a good argument about it, there's nothing really that you can say. I mean, why is that the default position? I don't know. So in the same thing with the drug testing case that I've been talking about. So why is it the default position that a drug doesn't make any difference, that it doesn't cure disease? Well, maybe there's a little bit of a better reason there. Why might you do that?
Either to prove that it does,
Yeah, so
or something to,
it has something to do with the burden of proof, right? It seems like it's up to us to prove that the drug does do something. We don't start under the assumption that the drug cures everything and then try to wipe away with everything. So maybe in some cases, it seems like there is a good reason for your default position. But all that to say, default position is a philosophical issue that people deal with sometimes. All right, so questions on the null hypothesis? All right, so another definition an alternative hypothesis. What do we think this is going to be, just based on the language?
Another hypothesis that's different from the null hypothesis?
Exactly. So an alternative hypothesis is a hypothesis that differs from the null hypothesis. And sometimes I'll just call the null hypothesis just the null. And actually, I'll give you some notation. So the null hypothesis is usually denoted H0 or H naught or H null. I guess you can say all those things. You can read that as all those things. So H0 is the null hypothesis. You can think of 0 as something like the starting point, right? And then the alternative hypothesis is denoted H1, or sometimes you'll see it as HA, A for alternative. I'll probably just use 1, H1. Just means that it's different from H0. And so, in the example that we had here, this was the null hypothesis that the coin was fair. So what was the alternative hypothesis?
That the coin is not fair.
Right, so what does that mean symbolically? So,
If the probability of heads is less than or
I think you're on the right track.
less than half,
So,
or more than half.
what does it mean for it not, so what does it mean for it to be fair? It means that the probability of heads is 1/2. So what does it mean for it to not be fair?
Anything over or under 1/2.
Anything above 1/2 or anything below 1/2. So that would be something like the probability of heads is not equal to 1/2. So this is one way to write it. Or another way that you can write it would be the probability of heads is greater than 1/2, or the probability of heads is less than 1/2. So you have some freedom in writing your null hypotheses or alternative hypotheses. And so by the way, I posted the next worksheet, worksheet 7. It'll be your last worksheet. So you'll all be very happy about that.
Lucky number 7.
So it's your last one. The bad news is there's a lot of pages to it. But I leave you a lot of space to do things, so it's really not that bad. And we may not get to the last question, though I'm going to shoot for doing that. So the last question comes from chapter 10. We're going to skip 9 and parts of 8. But we should be able to get to it. So there's a lot of space here. The first question asks you, I give you some statements, and I ask you to identify a null hypothesis and an alternative hypothesis. And you could do it symbolically. This is the easiest way to do it. So here, with a fair coin, which might actually be one of them, null hypothesis. So your null was 1/2, and this was your alternative hypothesis. So you'd have to try to do that for the rest of these questions. All right. So just a note, sort of writing down what we've been saying a little bit. When we do hypothesis testing, we assume H0, the null hypothesis, and gather evidence to test whether it's true or not. So gather evidence to test whether we have reason to reject it. And what are we rejected in favor of? The alternative hypothesis, right? And there's not really much you can say if you reject the null hypothesis in favor of the alternative, right? It's not like you can say, oh, well, the probability of heads is not 1/2, oh, it must be 1/3, right? You can only say that it's less than or greater than 1/2. And then you might conduct another test, right? Is it equal to 4/3 or something, or 3/4, and then check that. Yeah, so what we really need to do is characterize what we mean by rare, right? So if some test statistic is rare with respect to the null hypothesis, then we're going to reject it. So that's the next thing we want to do, is characterize what we mean by rare. And first, I'll give you some test statistics that we're going to care about over the next class or two, and then we'll talk about how we assess whether they're rare. And as we go along, if you see relationships between this and confidence intervals, you're not crazy. They're closely related. So the test statistics that I'm about to give you are very similar to what you've seen for confidence intervals. So when deciding whether a sample statistic is rare, we're going to calculate a test statistic. So by sample statistic, I mean just something about the sample. So could be a proportion, could be a mean, could be a standard deviation, could be a median, a mode, something like that. Oh yeah, I missed that. Is rare. And so I'll give you, so the main parameters that we've been talking about have been proportions, means, and, well, proportions and means. So we haven't talked about test statistics or estimating variances yet, and we probably won't. So these will be the main ones. But there are two cases for means, so remember the two cases. So remember in confidence intervals when
we know the,
Standard deviation?
yes, and when we don't know the standard deviation. So we're going to have one test statistic, which I'm going to call TT, which is the test statistic for a proportion. So this should look somewhat familiar. And so remember, p hat is the sample statistic, the sample proportion. P is the true proportion, and n is the sample size.
and we said this is the test statistic for proportion?
Yeah, so test statistic for proportion. And so I'm not sure, well, can anybody guess what the distribution of this test statistic might be? So by distribution, I mean, if you took a whole bunch of different samples, this p hat is going to change. So that means this quantity is a random variable, and it's going to have some distribution. So binomial, t distribution, normal distribution. What do we think? Anybody have any guesses? So
Normal.
So it should be normal. Why? So remember in your formula for, so we didn't derive it.
Yeah, because you're figuring out P. And P hat is a sample of your population. So those were normally distributed.
Yeah, so remember the picture that I just had on the board was a normal distribution, and we said that p hat has a normal distribution with whatever the true mean is as its center, as its mean, and it has some standard deviation. Well, here we're subtracting off the mean and dividing by its standard deviation. So this is just like a z-score. So this should be normal 0, 1. And another way that you can think about that is, remember the formula for confidence intervals has z-scores in it, right? And that should point to the fact that this is normally distributed. So if it has z-scores, the thing in between when we, well, I don't want to write it, but when we write out the confidence interval for proportions, we have z's in it, right? Z alpha over 2. Well, that's because this is normally distributed. All right, so this is the test statistic for proportions, and I'll give you one for mu, the mean. Can anybody guess what this one might be?
Yeah.
You can? You don't want to tell me?
Oh, I said T, so it's M or S, but, you know.
Oh. How do I want to denote this?
How much does it know if you don't know how to know?
Well, I know what it is, I just don't know what kind of notation I want to use.
Oh, okay.
See, here I use P, so I guess I want to use mu
Yeah.
and sigma. That's what you were using.
That's what I have written down.
So what do we think? So does anybody remember, so if we're talking about mu, what's our estimate for mu going to be? A sample estimate. X bar. Does anybody remember the distribution for X bar? Central limit theorem? Oh, sorry. Did we talk about that?
No.
No. The, I'm drawing a blank.
Well, that was.
Not the central limit theorem, the other one. 6.5.
Oh, we just,
Well, we talked about the distribution of this. Yeah, it is the central limit theorem. I'm not crazy.
Is it mu and then the variance?
So mu, and what's the variance?
Oh.
Sigma squared over n.
Where are we at?
Yeah.
So this is the variance. The standard deviation would be sigma over square root of n. Right, so we saw this in 6.5, and it is the central limit theorem on that. So if this is normally distributed with this mean and this variance, how are we going to, what test statistic could we get that would be distributed normal 0, 1? What would we have to do? This is a good review of chapter 6 for the finals. So if these symbols scare you, think about something that's normally distributed with mean of, I think on the worksheet I gave you mean of 5 and standard deviation of 1, or variance of 1. What would you do to normalize it, to get it to a standard normal?
You have to do the same thing to each side, which was,
So this is the same as, you know, when you have something, so x bar is a random variable, and you want to find the probability that it's, say, less than 2.
it was x minus the mean divided by,
This is just calculating the z-score, even back from chapter 3. We've been doing this for a while. So it's whatever the random variable is minus the mean, right? So minus
x minus
mu.
the mean divided by, the sigma, right?
Yeah, so divided by whatever the standard deviation is. So if this is the variance, the standard deviation is what? So I just said it. Sigma squared n. Sigma over square root of n. So this is a test statistic for means. And it's distributed normal 0, 1. And what do we know about this test statistic? What do you have to know for this test statistic? What things do you need to calculate?
But you have to have either the standard deviation or the
So
variance.
this is a test statistic for mu when sigma is known. And this is a good question that maybe somebody's wondering. This has the true mean in it. This has mu in it. And this has p in it, the true population. If you're trying to estimate p, or if you're trying to estimate mu, then how do you ever calculate these things? It's a good question, right? You guys should ask me that question. So what we're going to do is calculate these things. Remember, we assume the null hypothesis. So we calculate these things under the assumption that the null hypothesis is true. So if the null hypothesis is true, how do we get these p and mu?
Well, if you're on the coin, then you go by your 1/2.
Exactly. So you assume something is true. In the case of a proportion, the example that we've talked about, if you're assuming the null hypothesis that the coin is fair, this p is just going to be 1/2, right? This p hat is going to be what? So it'd be the, what's that?
I said your experiment, like, you know, like if you flipped it 20 times and you got
Exactly.
none, you know.
Yeah, it's the sample proportion, so you take a sample, it's the number of heads you get out of.
It's like 5/20.
Yeah, right. And so this, notice, is p, so this is under the null hypothesis, whatever you assume p to be. And how do you get n? Well, it's just the number of the number of
Right.
units in your sample. So if you flip the coin 20 times, there you go. So here, if you're trying to guess, say, I think the book has an example like heights of supermodels. So you assume that supermodels have, they have good examples in the book. So you assume that supermodels have some height, right? And you want to know what that height is. Well, assume it's something. Calculate the mean for some sample. And here you have to assume that you know sigma, right? We're not trying to find this, we know it. Divide by the number in your sample, square root of the number in your sample, and that's your test statistic. So you have everything you need because you're assuming you know these things under the null hypothesis. And so the last one we'll look at is what is the test statistic for mu when sigma is unknown? So it's going to depend on mu and what? So what do we do when we don't know some parameter? Yeah, so we estimate it from a sample. And so what's the estimate for the population standard deviation? S, right? So again, this should all look familiar from confidence intervals. And so what do we think the test statistic is going to be here? X bar minus what? Yeah, mu.
And it's gonna be S over.
Divided by S over the square root of n. And does anybody remember the distribution of this? We talked about this not too long ago. T distribution, right, good. With how many degrees of freedom? N minus 1. You guys are good. So these are the main test statistics we'll use. And just like in confidence intervals, we skipped confidence intervals for sigma itself. Here we're also going to skip hypothesis testing for sigma or sigma squared. But just know that you can do it, right? If you really want to, you can read 7.5. And so maybe I'll remind you now in a note that you get mu and p from the null hypothesis. Remember, mu, the true mean, and p, the true proportion, are calculated under the null hypothesis. And when I say under the null hypothesis, I mean under the assumption that the null hypothesis is true. So it's just a way to write that shorthand. All right, so once we have these test statistics, well, we have to assess them, right? Remember, the goal is to find out whether these things are rare under the null hypothesis. So we have to talk about assessing test statistics. So basically the idea is going to be this. So the null hypothesis is going to have some distribution associated with it. So the null hypothesis is that the coin is fair. The distribution, remember, is going to be normal, where the mean was 1/2. Right? This is the distribution of p hat. And we want to assess whatever test statistic we calculate by designating a region to be considered rare. So this region would be rare, right? Because if the true mean is 1/2, and we calculate a sample where we get, 2 heads and 20 tosses, this would be rare. If we calculate another sample proportion where we get 18 heads and 20 tosses, this would be rare. So we care about usually the tails of the distribution, and we want to find some criteria for choosing a value here and choosing a value here, such that if your test statistic is above that, we call it rare, and we reject the null hypothesis. So that's where we're going.
When you just use your standard deviation?
Yeah, so it's going to be related to that, yeah. So we're going to, basically what we're going to do is, first, how do we choose how far out we go?
Didn't we
determine that 2 standard deviations.
was outside the norm?
use that?
So that's one rule, right?
Are there more that we're going to learn?
Calculate the area and look on the Z-score, or?
Yeah, so when we talked about something being rare back in whenever that was, chapter 3, why did we choose 2 standard deviations? Because I said so. Well, in a
I know there's
That
a
was
reason, I
important.
just don't remember what it was.
So in a normal distribution, does anybody remember the percent that falls within 2 standard deviations?
95.
So 95, right? And remember when we were calculating confidence intervals, a lot of times I would give you alpha 0.05, which is a 95% confidence interval. And what was Z alpha over 2? For alpha 0.05. So what was it?
1.96.
1.96. And what is a Z-score?
The area under the curve.
Number of standard deviations.
Oh.
So it's the number of standard deviations away from the mean. So in this case, this value we've shifted to 0, right? This is a standard normal. And look how close that is to 2. So that's really the reason why, before we started talking about this normal distribution stuff, I just said, hey, look, more than 2 standard deviations is going to be considered rare. It's because, well, when we calculate out, it's really 1.96 is 95% in between and 5% out. 5% is rare. So either we care about 2 standard deviations away, or we care if the probability is small. So this probability is alpha over 2. This probability is alpha over 2. This is negative Z alpha over 2. You guys are getting tired of seeing this picture, right? And if alpha is 0.05, then 5% of the time we're going to say it's rare, and the other 95% of the time we're going to say it's not rare. So this holds for confidence intervals, and it's the same type of story for hypothesis testing.
So there isn't a whole lot in new stuff. We've seen a lot of it.
You can think of it that way. I mean, we're getting some new terms, and I mean, a lot of people, not just statisticians, but a lot of scientists, engineers, social scientists, doctors, there's a lot of people in the medical field use hypothesis testing as opposed to confidence intervals. And statistically, mathematically, they're very similar, but I don't think most people think of them as this similar. So So some people do hypothesis testing, that's why we introduce you to the language of hypothesis testing. Some people use confidence intervals, that's why we introduce you to that language. But they're very closely related. So a rejection region is a way that we're going to assess a test statistic, and it's just going to be this region out here, right? The set of z-scores, say, that give you, say, less than 0.025 over here if alpha is 0.05, and greater than over here. So the nice language that I have in my notes.
So again, it's just 1 minus alpha
Where?
to give you your 10%. Or your yeah.
So this
Your,
area
well, your
is
5%,
95%.
sorry, yeah.
So 95% of the population we say is normal or not rare, and then 5% out on either tail we say is rare.
But again, to get your 95%, it's 1 minus alpha.
Yes, yeah, that's right. Yeah, so it's 1 minus alpha over 2 minus alpha over 2, which is just 1 minus alpha. Exactly. So a rejection region is just a set of all values that cause us to reject the null hypothesis. And so you can imagine calculating this value, right, and it being greater than 1.96. So in that case, you would reject the null hypothesis. And if you calculated this value and it was less than negative 1.96, you'd also reject the null hypothesis, because it would bring you either here, somewhere out this way where the probability is very small, or somewhere out this way where the probability is very small. So we're just comparing our test statistic to a rejection region. And then the next thing to be introduced to is just a significance level, which just means how do we choose alpha? So alpha is basically your significance level. So, yeah, I'll erase this. I'll probably have to draw it again. So a significance level is the probability that the test statistic will fall in the rejection region. So, can you imagine, what have I left out of the statement? What's important that's being assumed here? So in order to calculate a test statistic, and in order to find a rejection region, what are we assuming? Yes, the null hypothesis. So we fail, that will fall in the rejection region, assuming H naught is true, right? And so what happens if a test statistic falls in a rejection region? And we have evidence against the null hypothesis, right? At significance level, whatever we choose it to be. And so what are common significance levels?
Would it be your 90, 95, and 99?
So the opposite of those.
Oh.
But you're thinking correctly. So significance level is alpha because it's the probability that the test statistic falls within the rejection region. So that's going to be out at the tails. So say alpha being 0.01. Alpha being 0.05, maybe alpha being 0.1. And why is that true? Well, just think about what this statement says with respect to, say, the standard normal. I knew I drove through that. So if alpha is equal to 0.05, then the probability that the test statistic will fall in the rejection region is just the area under the curve to the left of this score and to the right of this score. So the significance level is the alpha, right? It's the probability that it will fall this way. So it has to be this alpha, where this is alpha over 2, right, and this is alpha over 2 for this alpha level, 0.05. So here, the significance level in this example,
0.05.
right, so the significance level in this example is 0.05, it's the alpha value, because it's the probability that it falls in this rejection region, right? The rejection region is where the test statistic would be considered rare. All right, and the last thing that we need...
Is that last one, sorry, 0.1?
Yeah, and so really these things are discipline and context dependent. Why would you choose 0.01 as opposed to 0.05 or 0.1? So it depends on what you're studying.
You want to widen or narrow your...
Right. So imagine if you were assessing some chemical that we were going to use to put in our food, maybe to make our food grow faster. Do you think you'd want to choose a high or low alpha value to choose the test on whether the chemical is harmful to people? So think about what it would mean. If you chose a bigger alpha, it would bring these values in, and your rejection region would be larger. So say you started under the null hypothesis that this chemical, say, doesn't harm anyone. Would you want to reject that often? Would you want to be really careful and maybe...
Sure. I would have choose the 0.01 instead of the 0.1. Maybe I'm backwards.
So I think you're backwards. So you would want to choose, you would want to be alerted more frequently that the chemical is harmful, right? So if the chemical is harmful, you would want to know earlier, which means you'd want your rejection region to be tighter, a bigger rejection region, so you'd want this region to be tighter.
That would be the 0.1, right?
That would be 0.1, right? That would be, you'd be alerted more often, right? The probability would be higher that you would reject the null hypothesis that the chemical is not harmful. And of course, you could set up the experiment different, right? You could say, the chemical is harmful, let's try to prove that it's not harmful. And in that case, you might want the really low alpha. And all this stuff has important, like, policy, I don't know if I want to say applications. It's important for making policies, right? The U.S. tends to put the burden of proof on us to say that the chemical is harmful. So we have GMOs everywhere in our food, right? And in Europe, they've sort of rejected GMOs, and they said, look, we're not going to have those in our food. Prove to me that they are safe, where we say, prove to me that they're not safe. So you can couch all of that in statistical language, and it has something to do with significance level. So maybe just to make a connection to the real world. All right, one last thing to define, and then we can do some examples. So do some things that are on your worksheet. Everybody hanging in there so far? Good. So the last thing that we need is a critical value. And we've talked about this term before too. So does anybody remember what a critical value is? Maybe pointing to this picture.
Well, a critical was a value of, like, has a significant value. So it's something that's fairly, like the 99% and the 95% was fairly just huge common.
Yeah, so I think you're on the right track. So what are this area and this area together, what do we call this? I mean, it's on the board. If you know what I mean. Oh, what? Rejection region, right? So I'll abbreviate that here in this picture as rejection region. So what might we call this region in the middle? If you calculated a test statistic and it fell, say, above 1.96 or below, above negative 1.96, below 1.96. If we don't reject it, what might we call it?
An accepted.
An acceptance region. And a critical value is going to be a value, something like a z-score, that separates the rejection from the acceptance region. So it's a value that separates the rejection region from the acceptance region. It should be in R. So I'll call this AR. All right, so let's do an example or two. So these examples show up, similar things show up on the first question of your worksheet. And the next class will be able to solve a lot more questions. What's that? Oh yeah, so we have another at least 5 minutes. Don't try to stop me now, I'm on a roll. So, here's an example. So using significance level alpha equals 0.05, find the two critical z-values for the hypothesis, so the null hypothesis that, say, the probability of a fair coin landing on heads is 1/2. So how would we do this?
Sure.
I mean, it's something that we've done in different scenarios 100 times.
Oh, C alpha over 2.
Yeah, so this is just critical z-values such that at significance level alpha, they split. So remember, critical values split the acceptance region from the rejection region. So you're going to have some acceptance region in the middle and some rejection region outside. So it's really just that picture over there. Again, our favorite picture. But it's important to do these examples because here you don't have what in the homework, you don't have what I wrote on the board 30 seconds ago. So you have to know the terms. So remember, the critical values are these values right here. So there are these values that separate the rejection region, so these values, from the acceptance region. And at 0.05 level, what are these?
1.16 and -1.96.
Exactly. So our favorite numbers ever. So what other kinds of questions could I ask you? So I could ask you things like, what are the critical z-values for alpha 0.01, different alpha values, right? And notice that this is what's called a two-tailed test. So why do I call this a two-tailed test? It should be obvious from the picture.
There's 2 tails.
So there's 2 tails, right? So what would a one-tailed test look like?
You only have one.
Let me see. I probably have.
You have either the right or the left.
Yeah. So what would a right-tailed test look like?
Right?
A tail on the right?
Longer tail on the right?
So you're right. It's going to look like this. The right tail is going to have the rejection region. And what is the value going to be here? If it's level alpha. So for any alpha. So what is the area here going to be? So alpha, right? And namely, not alpha
Still 1
over 2.
minus alpha.
Yes, so you want 1 minus alpha as the acceptance region. So that means you're going to accept whatever test this is testing, you're accepting really low values over here. But you're only rejecting when you get above some value. So this is going to be Z alpha. Right? Here, we split up the 0.05 into the 2 tails.
So it's alpha over 2 on this.
Right, so that's why it's alpha over 2.
So then the area on the right tail one, the area to the left is 1 minus alpha, right?
Exactly, or 0.95 if it was alpha equals 0.05. And then, so similarly for,
The left tail?
yeah. So a left-tailed test, we're going to have a rejection region on the left, and the rejection region is going to have significance level alpha. So this is going to be alpha, and this would be negative Z alpha. And that, again, makes this area 1 minus alpha. So you, again, see the parallels between confidence intervals and hypothesis tests.
So now on these, in real world, just for like reference, on here you're gonna say like if those were your 1.96, like close to your standard deviations there. So these guys, I'm just trying to correlate this to like real world. Like what would the alpha over 2 represent? Like would it be people cured, people like that weren't cured by the
So the
placebo
alpha over
or whatever,
2
like,
just represents the probability, so this is a significance level of alpha, so it's the probability that some test statistic is calculated and it's rare. So if you calculated a test statistic and it's greater than 1.96 as a z-score, then it's going to fall somewhere over to the right, right? And that will be the probability of the test statistic that you calculated under the null hypothesis. So it gets complicated when you think about what the null hypothesis is under real-world situations, and then what the probability distribution is under real-world situations. So things get difficult. And I assign 1 or 2 questions in the book where they give you a scenario and they explain, well, what are these critical values? What is the assumed probability distribution? So I would take a look at those questions. But let's have somebody out. You said you'd run and give the evaluations.
Right, so on the left, it's not -1 minus alpha, right? It's always just 1 minus
Where?
alpha. Like if you were to do the left or the right, it's the same.
1 minus.
So 1 minus
It's
alpha
just-
doesn't
Yeah,
change,
because
it becomes negative.
It's area, remember? So
Right.
area is always
Okay.
positive. So
Right,
this
right.
area is 1 minus alpha.
Right,
So
just make sure.
Keep your pencils out.
yeah, keep your pencil. Oh, and last thing, and somebody tell Alex if he doesn't get back in here, he's laughing, but I posted an assignment that will add points onto your lowest quiz, and it could make your lowest quiz 100 if you do the assignment nicely. Actually, I didn't post it. I'm going to post it right when I get home.
So if we take our lowest quiz and turn it into 100, do you still drop the next lowest?
Yeah. So I'm being quite a pushover, that's for sure.
Thank you.
Yeah, so I'm going to post answer keys to
That's just like,
or the next.
oh, the previous exam.
Yes.
Did you ever happen to
I've made a rough draft of your final exam. It's
No.
very nice.
Unfortunately not. I'm sorry.
Okay, all right.
Yeah, it's just, she's gone, so she asked me to record. No, I don't, but I did take really good notes, so if you need the notes.
I do.
You do?
Do you mind?
Yeah, you can make a copy of it. Yeah, that's fine.
So, veteran Red Rock student,
Yeah.
is there anything that you need to know, like a code to write down on this thing?
I don't.
No, they should already be all printed out,
It should be on there.
and then you don't need to,
Everybody
you
knows
don't put your name or anything.
I don't have a pencil,
But
so.
you need a pen. You need a pen for it.
Pencil, pen.
It's
Everyone I've done so far has been a pencil.
It says pen when you read the instructions.
Have all the info.
All right. Either way.
That's
05.
okay, I have some pens, because you're not allowed to use a red pen, it has to be black pen.
Are you sure you didn't write all little?
Huh?
You sure you didn't write all the super little, the clean and no card?
No, I did not write all super little. I swear, I promise. Cross my heart.
Unless they keep it in the black